You'll find them in your phone charger, on utility poles, and inside massive power stations. They're the silent, static workhorses of our electrical world. And let's be honest, without them, modern life would just grind to a halt. So, how exactly do these simple boxes power everything?
Well, let's dive in by starting small, really small. Think about your phone or laptop charger. That little box takes the high voltage from your wall and somehow turns it into the low voltage your device actually needs. But how? There are no moving parts. The secret is some pretty incredible physics all packed inside a device called a transformer.
So, at its core, that's really what a transformer does. It moves electrical energy between two circuits that aren't even touching each other. The magic that bridges this physical gap, it's a phenomenon called electromagnetic induction, and it all kicks off with this fascinating relationship between two of the most fundamental forces in nature.
So, to really get how energy can just leap across a gap like that, we need to take a quick look at the fundamental link between electricity and magnetism. It's a two-way street, and it is fascinating. Okay, so here's the first key principle. Anytime an electric current flows through a wire, it generates this invisible magnetic field all around it. You can almost picture it like ripples spreading out in a pond. But for a transformer to actually work, the type of electric current you use makes all the difference in the world. And here's that crucial difference. Direct current, or DC, like what you get from a battery, it flows in one steady direction. This creates a constant, totally unchanging magnetic field. But alternating current, or AC, the kind that's in our walls, is constantly reversing its direction. And because of that, it creates a magnetic field that's also constantly growing, shrinking, and flipping. And that constant change, that's the whole secret. And honestly, that's the whole secret right there. It's not the magnetic field itself that's doing the heavy lifting, but the fact that it's constantly changing. A moving magnetic field can actually influence other things nearby. And that right there is the key to induction. So here's how it all comes together. First, that AC power enters a primary coil of wire, creating that pulsing magnetic field we talked about. This field then expands outwards, and it cuts across a second, totally separate coil of wire. This moving magnetic force, it essentially pushes the electrons in that second coil, creating or inducing a completely new electric current. Power has just jumped from one coil to the other, without them ever touching. Wild, right? But just transferring power is only half the story. The real genius of the transformer is its ability to change the voltage, and it does this with just three simple parts. Okay, so a basic transformer has three parts. You've got the primary winding, which is where the AC power comes in. Then there's the secondary winding, where the new current gets created. And connecting them both is the iron core. You can think of this core as a kind of magnetic superhighway, efficiently guiding that magnetic field from the first coil right over to the second one. All right, now that we have our components, we can perform the transformer's main trick, changing the voltage. And this is exactly where we get the terms step up and step down. The way it changes that voltage comes down to a really, really simple but powerful idea, the ratio of wire turns or loops on each coil. This turns ratio is everything. And it's surprisingly straightforward. If the secondary coil has fewer turns of wire than the primary, the voltage goes down. That's a step-down transformer, just like in your phone charger. And if the secondary coil has more turns, well, the voltage goes up. And you guessed it, that's a step-up transformer. And the relationship here is perfectly proportional. The ratio of the voltages between the coils is exactly the same as the ratio of the turns. So let's say the primary coil has 100 turns, and the secondary only has 10. The voltage drops by a factor of 10. It's really that simple and that predictable. But wait a minute, if we can just increase voltage, aren't we just creating energy out of nothing? Not at all. The law of conservation of energy says you can't get more power out than you put in. See, power is voltage times current. So if you step up the voltage, the current has to step down by the exact same proportion to keep the power equal. It's a perfect trade-off. So, knowing all this, let's zoom out from that little charger on your desk and see how these simple devices make our entire electrical grid possible. Okay, so at the power plant, giant step-up transformers boost the voltage to incredibly high levels. We're talking hundreds of thousands of volts. And why do they do that? Well, because sending high voltage requires much lower current for the same amount of power. And lower current means way less energy is lost as heat in those long transmission lines. Then, at a local substation, a step-down transformer lowers that voltage for distribution around your town. Finally, another smaller transformer, maybe on a pole or in one of those green boxes in your neighborhood, steps it down one last time to the safe voltage that comes right out of your walls. Now, you heard me mention an ideal transformer earlier, but of course, in the real world, nothing's perfect. So, how do engineers deal with the small amounts of energy that do get lost along the way? Well, the main problem is that the changing magnetic field doesn't just induce a current in that second coil, it also induces these tiny swirling currents inside the iron core itself. These are called eddy currents, and they're a key source of what we call iron loss. It's just wasted energy that creates heat. But the solution is brilliant. Instead of a solid block of iron, the core is built from very thin, insulated sheets, all laminated together. This breaks up those little whirlpools of current, drastically cutting down on energy loss and making transformers over 99% efficient. And that's really the story. From that tiny brick that charges your phone to the massive units that power entire cities, the transformer is just an elegant, efficient, and absolutely essential device. With zero moving parts, it simply uses the fundamental laws of physics to step voltage up and down, making our entire electrical world possible. It just goes to show you that some of the most important technologies are the ones we never even notice. It makes you wonder, doesn't it? What other simple, brilliant inventions are out there, hiding in plain sight, just silently making our world work?